By the way, guys, if you didn't watch the previous video, take some time out and watch it because there's a significant amount of information on there about those rational functions. And some of it I am going to go over again because I'm talking about the rational inequalities. So if you haven't watched that video, please go in and watch the video. And guys, whether you believe it or not, the videos actually help, okay? So you need to go in there and try to see if you can watch the videos. And well, it's technology. You can fast forward through the entire thing, you know, put it at 1.5 speed or something and quickly move through it and then see what you need to really pay attention to and then slow it down there, you know? Okay, so use the technology. So guys, here we are, lesson 3.6, solving polynomial inequalities and rational inequalities, guys. So we're going to start off with the polynomial inequalities. And so these are pretty much just like equations, guys, but what is the difference? Rather than getting exact solutions, you know, 1, 2, 3, or 4 solutions, or whatever number of solutions here, you're going to have a range of solutions, And once we start talking about these range of solutions, guess what you're going to have to do? You're going to have to write the solution. Oops, let me go back just a little bit here. Write the solution in interval notation, guys. So this requires you writing the solution in interval notation. And guys, as we do this, pay attention. I will be showing you which questions you're going to see on the test. And remember, most of the tests will be for response. You will not be getting too many multiple choice questions on the test. So you have to know what you're doing, okay, guys? So here are some steps for solving the polynomial inequalities. Number 1, you want to go ahead and isolate the polynomial. Either set the polynomial so that it's greater than 0 or it's less than 0. So isolate the polynomial first, guys. Either you set it greater than 0, greater than or equal to 0, same thing, less than 0, or less than or equal to 0, same thing. Now, number 2, you want to factor the polynomial. And the problems that you will encounter, guys, they're all factorable. If it's not factorable, there are other ways to solve polynomials, but these right here, they're factorable, okay? Number 3, on this one right here, guys, you want to set each factor equal to 0 and solve. Now, this is a little different, guys. When you solve, you get these zeros. We don't necessarily call them 0. We call them critical values or boundary values. Critical values or boundary values. Once again, guys. So once you set the polynomial equal to 0, set each factor equal to 0 and solve, those values that you're finding, refer to them as critical values or boundary values. And I'm going to show you why we refer to them as critical or boundary values. Here's why. You're going to have to take those values, guys, and plot them on the number line. Plot the critical or boundary values on the number line. Now, next, guys, you want to go ahead and test each region. By the way, I did this already when we talked about the linear inequalities. So this is very similar to what we did with those linear inequalities, guys. So you're going to test each region to find the region containing all the solutions, as in containing all the values that would make the inequality true. So what you have to realize is that, guys, when you're testing these regions, the truth values, they typically alternate. Truth values, they typically alternate. Typically, notice I'm saying typically. I didn't say always. They typically, for the most part, alternate. As in they go true, false, false, true, and so forth and so on. So when you do this, guys, be careful. And then the last step is to go ahead and write the solution. There I go again. Write the solution in interval notation. All right, guys. So I'm going to go over a few examples, and as we do this, I will mention the ones that you're going to see on the test. So pay careful attention. Now, this one right here, it's too easy to be on the test here. You will not see it on the test, okay? Number one. Now, for this polynomial, it's already in factored form. X minus 7 times x plus 3 is less than or equal to 0. For this particular problem, guys, since it's already factored, you're done with step 1. You're done with step 2. So step number 3, take each factor, set it equal to 0, and solve. So we can find those boundary or critical values. So what value minus 7 makes it 0? Positive 7. What value plus 3 makes it 0? Negative 3. So there's your two critical values. So now you're going to go on the number line, guys, and you're going to plot these two values on the number line. You got a negative 3, and then you got a positive 7. Now, what this does is it breaks it up into 3 regions. So you've got a region to the left of negative 3. This should be very familiar to you because we did it back in chapter 1. Region 2 in the middle, and then region 3 on the right. So your job is to find which region contains all the solutions that will make the inequality true. And of course, you got to go ahead and test. And when testing, guys, the best value to start testing with is 0. 0 is in between negative 3 and 7. So you take the 0, go back into the original problem right here, and plug in 0 for every x. So if you plug in 0 into the first parentheses, you get negative 7. Into the second parentheses, you get 3. So you're multiplying a negative times a positive, which is going to give you a negative. So that means that this region in the middle, guys, it's true. That means every single value between negative 3 and 7 will make this problem true, okay? And remember, the truth values, they typically alternate. So if the middle region is true, then this means that the region to the right will be false, and the region to the left will also be false. So the region where we're going to find all the solutions that would make this inequality true would be in between negative 3 and 7. So we're going to graph it. I forgot to mention that in the notes. You got to graph it and then write the solution interval. So that should have been step number 6. Graph it, write the solution interval. So guys, we're going to graph it. Now, look at the inequality symbol here. Let me use a different color. Look at the inequality symbol here. That tells you whether to include or exclude the boundary values. So the boundary values will be included, guys. So we're going to go ahead and show that this is where all the solutions are that would make the inequality true. So you got your graph, and then you have to write it in interval notation. So the interval notation, starting from left to right, you're going to do bracket with the negative 3, comma, 7, close it off with a bracket. And guys, that's it. Okay, this one is not on the test. It's too easy. So here's one that could potentially be on the test, guys. Hold on a second. There's a few questions on here. Yes, the test is going to be on Zoom. Okay. What kind of numbers does the middle represent? Well, that's where you find all the solutions that would make the inequality true. So every number from negative 3 included up to 7 included will make the inequality true. So whole numbers, decimals, fractions, in between negative 3 and 7. Now, guys, here is the potential question on the test. Number 2, 4x squared plus 7x greater than negative 3. This one requires a little bit of work. First and foremost, guys, you need to isolate the polynomial, as in set the polynomial greater than 0. So you're going to take that negative 3, move it over to the left side, so it's going to become a positive 3, and all of this will be greater than 0. So now the polynomial has been isolated, so we're going to have to factor the 4x squared plus 7x plus 3. So to factor this, okay, we're going to go ahead and split up the 4x squared into 4x times x, I believe, will work. And the positive 3 will be plus 3 and positive 1. Now, I like to do a quick check, guys. Let me do a quick check. 3 times x, that's 3x. 4x times 1 is 4x. When we add them together, does it give us the middle term? Of course it does. So that means that the factoring works. And so we got our factors. Next, we're going to take each factor, set it equal to 0, and solve. All right. Let me see. Yeah, I'm still getting an echo. Hold on, guys. I'm trying to get rid of the echo. All right. Yeah, there's still an echo there. Okay, guys. So I'm setting each factor equal to 0. Where did I get that 3 from? Shazam, okay? And then I'm going to solve this. So what value plus 1 makes it 0? -1. Now for this one right here, it requires a little bit more work. So we get 4x equals to -3. You want to divide both sides by 4. So this results in x equaling to -3/4, guys. So there's your two critical values, -1, -3/4. So now you want to head over to the number line and you're going to plot these two values on the number line. So remember, guys, when you're plotting these on the number line, this is just telling you where your values are. So be careful with this, guys. You're going to plot your -1. These are just boundary values, okay? -3/4. Your 0 is going to be over here. Now remember, this divides up the number line into 3 regions. Oh my goodness. Just like the previous problem, it divides the number line into 3 regions, guys. So your job is to figure out which region has the solutions to this problem. And of course, guys, whenever you're testing these, the best number, unless it is a critical value to test with, is 0. So I'm going to take the 0 and go back into the original problem, which I erased, of course, and plug in the 0 to see what happens, guys. So if I plug in 0 for every single term, this term is going to cancel out. This is going to cancel out. So what am I going to be left with? 0 is greater than -3. So that means that this region right here is true. So if the truth values are alternating, that means the middle region is false. And the left region is going to be true as well. So pretty much this is telling us there's a set of solutions from -infinity up to -1. And then another set of solution from -3/4 up to positive infinity. Now guys, be careful with the inequality symbols. So here the inequality symbol determines whether or not the boundary values are included or excluded. And according to the inequality symbol here, you do not want to include the -1. So this is what the graph would look like. And you do not want to include the -4. So you would go ahead and shade the right side. So there's your graph. And now you got to express this in interval notation. So in interval notation, guys, you have a set of values from -infinity up to -1, not included. And then another set of values from -3/4 up to positive infinity. And of course, positive infinity is excluded. So guys, this is the kind of question you could potentially see on the test next Thursday. So take a moment, look at this one and see if you have any questions about it. Nothing? All right, guys. So let me go ahead. Let me see. Yeah, I am going to do another one. All right, so here's a third example, guys. And this third one right here is x to the third plus 7x squared minus x minus 7 is less than 0. Now, this one is a third degree polynomial. It has 4 terms. And so when you have these third degree polynomials, these 4-term polynomials, it's best to try and see if you can factor it by grouping. Somebody, I don't remember if it was in this class, somebody says, I love factoring by grouping. Yes, factoring by grouping is very interesting. It doesn't require that much work, that's why. So guys, we're gonna factor this by grouping. By the way, I want you to notice the polynomial is already isolated It's already less than 0, so you don't have to do that step. So you move on to step number 2 and try to factor, guys. To factor this, we're going to factor by grouping. So we're going to group the first 2 terms and group the last 2 terms, okay? That just means you put parentheses around them. The first 2 terms have an x squared in common, so you factor it out, and that leaves you with x plus 7. The last 2 terms have a -1 in common, you factor it out, that leaves you with x plus 7. Now, you want to factor out the x plus 7, so you'll be left with x squared minus 1. The x squared minus 1, guys, is a difference of squares, so you might want to go ahead and factor that into 2 binomials as an x plus 1, x minus 1. And so now you can find the critical values. So what number plus 7 makes it 0? -7. What number plus 1 makes it 0? -1. What number minus 1 makes it 0? +1. So guys, there's your 3 critical values. So now you're going to have to graph those 3 values on the number line, test each region, and then find the solution regions, the regions that have all the solutions, that contains all the solutions. So guys, let me go ahead and graph this. I'm just going to erase part of this so I can leave the polynomial on the screen. So let me go ahead and erase some of this right here. Okay, so now we're going to graph. So on the number line, here's your -7, your -1, your +1. Of course, 0 is right here. This divides the number line this time, guys, into 4 regions. Okay, 4 regions. 1, 2, 3, and then 4. And of course, guys, ooh, Shazam. I just momentarily forgot how to write a Roman numeral 4, huh? Okay, so guys, the best number to test with always is 0, unless, of course, it's part of the critical values. If it's not, test with it. Okay, so we're gonna take the 0, guys, and plug it into the into the original equation. I was just thinking about something, and I'll show you it to you guys in a minute. Okay, when we plug that 0 in, guys, this means that we're going to end up with 0 here, 0 here, 0 here. So we'll end up with a -7 is less than 0. Is -7 less than 0? Absolutely true. So that means that this region right here is true. Since the truth values are alternating, this region is false. This region is true. They're alternating most of the time now. Okay, guys, if you're not sure, what should you do? Just go ahead and plug in another value. Okay, for example, if you're not sure this last region, region 4, is true, plug in a value, plug in 2 into the problem and see what happens. So if you do 2 cubed plus 7 times 2 squared minus 2 minus 7, what does that give you? 2 to the 3rd power is 8, 2 to the 2nd power is 4, 4 times 7 is 28, minus 2 minus 7, is this going to be less than 0? 8 plus 28, that's a large number. That's going to be 36. 36 minus 2 is 34. 34 minus 7, that's going to give you 27. Is 27 less than 0? I don't think so. Okay, so this verifies that this region right here is false. Okay, so that's the validation you needed, guys. So now we know where the set of solutions are occurring. So we're going to go ahead and graph this in, guys. Don't forget about the inequality symbol. So the inequality symbol is telling you the boundary values are excluded. So you want to use parentheses at all the boundary values. So guys, when we graph it, this is what the graph is going to look like. And then of course, you got to express this in interval notation. So in interval notation, guys, you're going to end up with -infinity up to -7 not included, and then union from -1 to +1 not included. All right, guys. Now, I know some of you are probably thinking, or maybe I'm hoping you're thinking this, okay, that this is a 3rd degree polynomial. What does this have to do with the graphs of a 3rd degree polynomial? That's what I wanted to mention to you guys, okay? So for this problem, just quickly, guys, which we can do on the graphing calculators. By the way, you can graph inequalities on the graphing calculator. And since this is a 3rd degree polynomial, you got a critical value at -7, okay? And then you've got another one at -1 and another one at +1. Guys, remember the end behavior on this one would be down on the left, up on the right. So it rises on the right, falls on the left. It's a positive x cubed graph. So guys, pretty much the graph would look something like this. By the way, the actual line itself, it is not a solid graph. So this is what the graph would look like. So when you go and shade this in, guys, this is what the shading would look like, something like this, okay? Yeah. So if you were to graph this on your graphing calculator, this is what it would look like, that inequality graph. Yeah. Anyways, I just wanted to mention that to you guys because it's worth mentioning since we were talking about higher degree polynomials and their graphs. All right, guys. So the next question I'm going to ask you is this. If you see a problem like that on the test, okay, are you able to find those critical values, plot them on the number line, and find the solution region? If you're not able to do that, guys, you need to be asking a question. And remember, that's the type of question you're going to see on the test next week. All right, so seems like you guys don't have any more questions, but of course, the video is there, guys. You can always go back over it. Now, I am going to move on to the second part of the lesson, which is the rational inequalities, guys. Now, for the rational inequalities, this requires some knowledge about the rational functions, which is in the previous video. So for these problems, guys, when we talk about rational inequalities, we're looking at inequalities containing fractions with variables in the denominator. So here is an example of what I'm talking about. X plus 5 over x minus 2 is greater than 0. All right? So that's the kind of problems you're going to see with the rational inequalities. First and foremost, guys, you need to find the restricted or excluded values or value. Now, this is the value or the number that makes the denominator equal to 0. So in the case of this problem, the denominator is x minus 2. What value would make the denominator equal out to 0? That would be x equals to 2. Now, this x equals to 2 becomes a critical value. So that's the first thing you need to do. And then the second thing you need to do is to solve the inequality, Now, guys, because this inequality is greater than 0, to solve it, it's very simple. You set the numerator equal to 0 and solve it. Set the numerator equal to 0 and solve. So guys, on this one right here, the numerator is x plus 5. We set it equal to 0 and solve. Remember, we're not solving it saying, oh, the answer is x equals to negative 5. We're just solving it to find the boundary value or the critical value. So now, guys, we're going to go to the number line and plot these numbers on the number line. We have a negative 5 and a positive 2. The negative 5 is the solution from solving it. And then you have the positive 2, which is the restricted value. Now, I did not put an X over here. I just realized that. So here, once you plot these on the number line, just like with the polynomial inequalities, you divided the number line into 3 different regions. So now your job is to figure out which region or regions contains the solution set to the problem. So guys, let's test it out. Why did you solve x plus 5 but not x minus 2? We solved x plus 5 because it's in the numerator. The denominator is there simply because you want to find the restricted value, the value that makes the denominator 0. Additionally, Sarah, if you're trying to solve this, this is a fraction, okay? When you're solving this, you would cross, you know what? Hold on to that thought. I'm going to come back and show you. Let me finish this part and I'll come back and show you. All right. So guys, on this one right here, listen. We're testing this. So if you take 0, you go back to the original problem, guys, and plug it in. You get 0 plus 5 in the numerator, which is 5. You get 0 minus 2 in the denominator, which is a negative 2. So you're going to have a positive divided by a negative. Is a positive divided by a negative going to be greater than 0, guys? I don't think so, because that's going to give you a negative. So this means that this region right here is false. So we're going to assume that this region is true and this region is true. But instead of assuming, why don't you go ahead and test the region, guys? So let's go ahead and plug in a different value. Let's plug in 4. If we take 4, we plug it into the original problem. 4 plus 5 is 9. If we take 4, we plug it into the denominator. 4 minus 2 is going to give you 2. 9 divided by 2, guys, is a nice positive number. 4.5. Is 4.5 greater than 0? Absolutely true. So it's good to verify these, guys. Even sometimes when you're sure, it's good to verify it. So this region is true, and this region right here is true. So the set of solutions will occur in this region right here to the left of the -5, everything to the left of the -5, and everything to the right of +2. So this is what the graph looks like. But then you have to express this in interval notation. So in interval notation, it's -infinity up to -5. Close the parentheses off. And then union +2 up to +infinity. Guys, you've got to be careful when you write these interval notation. Any questions, guys? All right. So let me leave this question alone and let me mention Sarah's question too. X plus 5, maybe somebody else has the same question. Okay. So first and foremost, Sarah, x minus 2 in the denominator, whenever you encounter these variables in the denominator, you have to start thinking about what value would make the denominator 0 so you can restrict it from being a solution, because the denominator of a fraction cannot be 0. Now, think about it this way, guys. If this was equal to 0, Sarah, okay, the question was, why aren't we solving x minus 2? In a way we did, okay, but this is a little different, okay? So when you talk about solving, my thought is solve the problem, solve the equation. How do I solve the equation? Why am I just setting the numerator equal to 0? So let's look at it this way. So rather than have the inequality symbol here, I'm just going to go ahead and change it to an equation, set it equal to 0. If I'm solving this problem, how would I solve this problem? I would multiply both sides by the LCD. Look at what happens when I multiply both sides by the LCD. X minus 2 cancels out with x minus 2. So that leaves me with x plus 5 on the left side. And 0 times anything is just 0. So pretty much I have the numerator and I set it equal to 0. Notice I'm saying for some of the problem, the only time this works is if the inequality is either greater than 0 or less than 0. If it's not, you cannot just take the numerator and set it equal to 0. There is a problem coming up where you cannot do that, guys. So I will show it to you very shortly, okay? So I am going to clear this out, guys, and let's do a secondary example. And you need to pay careful attention to this one, because this is the type of question you will encounter on the test. So here, the first question is this, guys. What's the restricted value? What value makes the denominator equal to 0? You are restricting that from being a solution, part of the solution set to this problem, okay? So the restricted value for this one is going to be a -4. Now this restricted value right here, guys, is going to become one of the critical values on the number line. Now, be careful. Here's why I'm telling you to be careful. We just said x cannot equal to -4, guys. But if you look at the inequality symbols, what is it? It's less than or equal to. The inequality symbol says to include the boundary values. But if we include -4, that would make the denominator equal to 0. So guys, here's why you need to be careful. When you're writing a solution set, you do not want to include the -4. So make sure you're using parentheses with the -4. Do not use the bracket. Why? If you use the bracket, you're saying it is included as part of the solution set. And if you're saying that, you're saying it's okay for the denominator to be equal to 0. And you know the denominator of a fraction cannot be 0. All right, guys. So now we have the critical value. Let's go ahead and solve the problem. And yes, this one, we can take the numerator, set it equal to 0, and solve it. We subtract 2 from both sides. We get -x equals to -2. So it looks like x will equal to +2. okay? So there's our two critical values. So now we go on the number line and plot them on the number line. We got a -4 and then a +2. And of course, guys, we're going to test each region to find the solution set for this problem. So on this one right here, guys, 0 is located right here. If we take 0, we plug it back into the original problem. In the numerator, 0 plus 2, that's 2. In the denominator, 0 plus 4 is 4. Is 2/4 or 1/2 less than or equal to 0? I don't think so. This region is false. Now, if you're not sure about the other regions, test them out, guys, like 3. If I plug in 3 into the numerator, okay, I'm going to get a -3 plus 2, which gives me -1. In the denominator, 3 plus 4, that's 7. Is -1/7 going to be less than or equal to 0? Absolutely true. So since the truth values are alternating most of the time, if this region is true, that means the region to the left is also going to be true. True, false, true. False, true, false, okay? That's the alternating sequence we're talking about. So guys, we've got the region where the solution set will occur. So we got a set of solution from -infinity up to -4. Can we include the -4? No, we can't. So we're going to use a parentheses with the -4. Okay, be careful with that, guys. However, we can include the 2, and that would include every value greater than 2. So when you express this in interval notation, it's -infinity up to -4, not included, union, every value from 2. Oh, I just put a negative there, guys. I caught myself. Okay, +2 up to +infinity. And there's your solution set. All right, I'm taking a little brief pause here, just in case you guys have a question, because I feel like there might be a question coming. I've got another one to go do. Okay, I'm gonna do another one. No questions? Guys, it's good to ask questions. Let me see here. Why can 2 be included? Because of the inequality symbol. And the 4 cannot be included because if you include, not the 4, the -4, if you include the -4, that would make the denominator of a fraction 0. And so the denominator of a fraction cannot be 0. When the denominator of a fraction is 0, it's undefined. In the last problem, we had a different inequality symbol. That's why. Yeah. The previous one was just greater than. This one right here, the commotion or the issue is that we have less than or equal to. And when you have less than or equal to, you're talking about including values, not excluding them. You're talking about including. So you can include the -4 because it's going to make the denominator 0. Yeah, so be careful with that. All right. Okay, guys, so here's my final example. Has anybody done the last homework assignment or that last quiz? And have you seen a word problem on there involving the perimeter of a triangle? Has anybody seen that?
No, not yet.
Okay. All right. Not yet you didn't do it, or not yet I didn't see that problem?
I haven't come across that problem yet.
Okay. Thank you. All right, guys. Now, this is a challenging problem. This will definitely be on the test. All right. So I want you to look at this problem carefully and analyze it, guys. What you will notice is that, unlike the previous 2 problems, there's no 0 in there. There's a 2 where the 0 was. So when we approach this, we're going to have to approach it a little differently. But just like with the previous problems, it's very easy for you to figure out the restricted value or the excluded value. What value makes this denominator equal to 0? -3. X cannot equal to -3. Okay, so we got that out of the way. Okay, that's good. Now, guys, we got to solve for this. So because that 2 is involved, that changes how you solve this problem, okay? So I'm going to show you 2 ways you can solve this. I'm going to start with the easiest way first, which the textbook doesn't necessarily like, but it works, okay? So we're going to pretend that this is an equation. Let's pretend it's an equation and then solve it. How do we solve it? We multiply both sides by x plus 3. By the way, guys, this is the same thing as putting the 2 over 1 and cross multiplying, seriously, okay, like a proportion, okay? So here, the x plus 3's cancel out, leaving you with x plus 1 equals to 2x plus 6. I'm pausing for a moment, just in case you have a question. Oops. All right, no question. So guys, what am I doing? I'm working with the 2. So now let's go ahead and finish solving it out. So on this one, I'm going to subtract x on both sides. So I get 1 is equal to x plus 6. Subtract the 6 from both sides. So I get x is equal to negative 5. So that is the value of x. Now, there is another way to do this. However, guys, I'm going to finish out the problem first, and then I'll go back and do it with you, okay? I'll show you the other way in a little bit. Give me a moment. Let me finish with this problem first. Okay. So now, guys, let's go to the number line. We're going to plot these critical values on the number line. We've got a critical value at negative 5, another one at negative 3. Now, don't forget, the inequality symbol is less than or equal to. This means we cannot include the negative 3. So we need to make sure we put parentheses around the negative 3. Okay, so be careful with that. Now let's test this. 0 is way over here, guys. If we take 0, we plug it into the original problem. In the numerator, 0 plus 1 is 1. In the denominator, 0 plus 3 is 3. Is 1/3 less than 2? Absolutely. 1/3 is less than 2. That means that this region right here would be true. Now I'm going to test with a different value, guys. I'm going to test negative 4. In the numerator, negative 4 plus 1 is negative 3. In the denominator, negative 4 plus 3 is negative 1. So when I simplify this, I get 3 is less than or equal to 2. Is that true or is that false? That's false. Remember, the truth values, they alternate most of the time. So if the middle region is false, then that means that this one right here is going to be true. Now, guys, remember, we can include the negative 5, but we need to exclude the negative 3. And why are we excluding it? Because we want to make sure it doesn't make the denominator equal out to 0. Simple as that. So guys, this is what the graph looks like. And now we're going to write our interval notation as negative infinity up to negative 5, which is included, union, negative 3 up to positive infinity. And that's it. Okay, so let me show you the alternate way of solving this problem, guys. Okay, let me just go ahead and erase this part right here. And who knows, some of you may prefer this method. Let's see here. Hold on a moment, guys. So here's another way you could solve the same problem, guys. You can take the 2, move it over to the left side. So this becomes x plus 1 over x plus 3 minus 2. Now we need to find the LCD. So remember, this 2 is over 1. The LCD would be x plus 3. So we'd multiply the denominator by x plus 3 and the numerator by x plus 3. Remember, whatever you do to the denominator, you must do it to the numerator. So this would become x plus 1 over x plus 3 minus 2 times x plus 3 over x plus 3. Now, guys, what you will notice is that the denominators are the same. We're going to keep the denominator and combine the numerators. So, guys, we have x plus 1 minus 2x plus, not plus, minus 6, because remember, we're distributing a negative 2. So this becomes a minus 6 is less than or equal to 0. If you want to keep combining this, you can take the x minus 2x. That gives you a negative x. And of course, you have a positive 1 minus 6. That's going to give you a negative, minus 6. Oh, Shazam, minus 5. Okay, let's fix that. Minus 5. And then that's less than or equal to 0. I forgot my denominator. My denominator is x plus 6. So guys, essentially what just happened, I took this and I transformed it to the previous two problems. So I isolated the rational inequality, okay? So the fraction is by itself on one side and it's less than or equal to 0. So now we can apply what we did to the previous two problems to solve it. We just take the numerator now, negative x minus 5, set it equal to 0 and solve. Okay, so you get negative 5 is equal to x. That's the same answer I found, but this is longer. This takes a significant amount of work versus just solving the equation, which still produces the exact same critical value. So your choice. It really doesn't matter how you do it. The goal is to find the value of x for the problem. Any questions, guys? All right. Let me see here. I should do this word problem right here, but I'm not sure if you guys are going to encounter it. So that's why I'm a little reluctant to do it. And I don't fully remember the gist of the problem, so I don't want to go ahead and just talk about this word problem without giving you exactly what the problem is trying to convey. So guys, rather than trying to go over this word problem that may not even be on the assignment, I'm just going to leave it right here and close off this recording, and then I will go ahead and take your questions. Okay, guys? So